Okay, hello everyone, and today we will finish the theorem we started last time, and we will hopefully have time to see at least one example of Gauss field localization, and then we will see more next time. So recall, so if E is a spectrum A is E acyclic if its E homology is trivial, that is, if E tensor A is 0, and the spectrum X is E local if for every A E cyclic, we have the mapping spectrum from A to X is 0. And here you can also put the mapping space, since you can replace A by its shifts, but we will use the mapping spectrum because it's more convenient. And the theorem we want to prove today is for every X spectrum, there exists a map. X goes to LEX, which is an E equivalence, by which I mean its cofiber is E acyclic, such that LEX is E local. This, remember, was the subcategory of E local spectra. In particular, for every E local spectrum Y, we have that the mapping space from LEXY is equivalent to the mapping space from X of Y, i.e. The inclusion E of E local spectra into spectra has a left adjoint. Okay. Is this statement clear? Also, I should say that LEX is sometimes also called XE, but I'll try to stick with LEX because I think it's a more widespread notation, but you might sometimes see also XE. Okay, so this is essentially a cellular argument, and for this we need the following result. Well, we need several finiteness results, but we start with the following result. Proposition. Sorry. Is someone talking? Okay. Proposition. Yeah.
Maybe I would have a question.
Sure.
The question gets asked once. So to promote this LE to a functor is really enough to give such a map. So there's.
Yes, because, okay, I didn't do a lot of details in higher category theory, but there is this result, let me call it a theorem, although it's overstating it. So if you have a functor of infinity categories, such that for every, what was it? Yeah, for every D in D, am I doing the right thing? Sorry, I might be doing the left or the right adjoint. Am I switching?
Yeah.
Whichever you're using.
No problem.
Yeah, okay, when this is co-representable, then F has a left adjoint. sending D to the co-representing element. You can try to prove it for 1 categories if you want to convince yourself that it's true. The proof is basically the same, only slightly more complicated for infinity categories. But it essentially follows from the unit embedding, right? So this functor sending D to this object, it's a map from D to pre-sheaves on C. And this is telling you that these lengths in the image of the unit embedding. And so this is factorial indeed. And then you need to, it's easy to see that this gives you an adjoint. And this works verbatim for infinity categories.
Okay, nice.
Sorry, I am sort of taking the strategy of sort of assuming standard category theory fact and applying them to infinity categories without giving the full proofs, but very often it's verbatim or verbatim with minor modifications. So I think I'm justified, and I think it's more important to see them in use, so then you can read the proofs for your own.
Yeah, I just wanted to point out that this theorem exists, so this really
Yeah. This theorem exists, and I think I also gave a sketch of the proof now, so I think everyone should be more or less convinced. Okay, so let me erase this. And actually, I already used this theorem implicitly, I think, when I constructed, well, at some point in the recognition principle, I think I used this theorem implicitly. I can put it here. Okay, so we need the following proposition. So let kappa, a regular cardinal, such that pi star E is less than kappa. And I might or may not have to assume that kappa is uncountable here. I'm not very interested in. So then every acyclic spectrum, every E-acyclic spectrum is, well, in fact, a kappa filter colimit, although we only care that it is a colimit of kappa small E-acyclic spectra. And why do we care about this theorem? Because this has a corollary that there exists a E-acyclic spectrum such that X is E local if and only if maps from A to E is 0. So I can check on one E-acyclic spectrum. And this will allow us to construct. And the proof is, well, let AI be the set. And by set, I mean I take one for each equivalence class of kappa small E-acyclic spectra, where kappa is as in the proposition. Then we let A to be just the direct sum of all AI, which now exists because it is a set. And that's why we all need to do all this dance and song with kappas, because we would like to take the direct sum of all E-acyclic spectra, but of course that's not something we're allowed to do. So now map AE is 0 if and only if map AIE is 0 for every I. And now if A prime is an E-acyclic spectrum, we can write map A prime E as the limit of map AI for some diagram of AIs. by the previous proposition. And so if map AE is 0, then map A prime E is 0. It's some sort of finitary or boundedness condition in being E local. In fact, when we will see the examples, we will see that it's fairly easy to construct these A's explicitly. Like we will find some very small and concrete objects that have this property, but this corollary tells us that they always exist. Okay, now should I do first the theorem using the corollary or the proposition?
Excuse me, Denis.
Yes.
So what's the role of X in this corollary?
Oh, that's because I am silly and I swapped E and X at some point. Terribly sorry about this. You must be extremely confused.
Now I'm no longer. Thanks.
I wrote E in the statement and then X in the statement and E in the proof, which is not something I was supposed to do. Okay. Remember this condition here is X is E local. The mapping spectrum out of every acyclic spectrum is trivial. Okay, I think I'm going to prove the theorem using the corollary, and then we will go back and prove the proposition. Okay. So remember, we have X and we want to construct L mapping to LEX, an E equivalence such that X is LEX is E local. So fix A as in the corollary. Then note that A is in spur. I want to call it kappa for some regular cardinal kappa. Which might be bigger than the previous one. And it's actually with the construction of A I gave you, it will be bigger, but it's not important. Remember that every spectrum is kappa small for some kappa. We proved this last time. So we are going to do a construct LEX by transfinite recursion up to level K. So how does this work? So we want that all the maps from A to X die. So we start with X0 equals X. And then we take X1 to be the cofiber of X of all the maps from sigma n A to X, where n is in Z and they're indexed by all the possible maps. And I mean, okay, all possible maps, I should be precise. I mean all possible homotopy classes of maps, of course. I choose one representative for each homotopy class. And then you go on. Precisely, I define X alpha plus 1 to be the cofiber, as before, of all maps to X alpha. And if lambda is a limit, so this is alpha ordinal, And if you have a limit ordinal, you just take the colimit. So I'm going on and killing everything. And the claim, so first of all, the claim that x to x alpha is an E equivalence for every alpha less or equal than kappa. We could continue for ordinals, but I'm going to stop at level kappa. And the other claim is that x kappa is E local. So x kappa is LEX. That is the claim. So, okay, the first claim is easy because you have the map x alpha to x alpha plus 1 is an E equivalence by construction. Since it's the cofiber when the source of the map is an E acyclic object. And of course, E equivalences are stable under colimits. So E goes to E lambda, which is just the colimit of the map from E goes to goes to X alpha for alpha less than lambda, is an E equivalence. So claim 1 is basically by construction. The important fact is that after we got up to level kappa, we managed to we managed to get an E local point. And the point is that these, so remember, x kappa is the colimit for alpha less than kappa of x alpha. And now the set of alpha that is less than kappa is, by construction, is a kappa filtered poset, because well, every time you have a subset of kernel less than kappa, you can find something bigger than that. That's just how things work. So we have that map A to x kappa is the same thing as the colimit for alpha less than kappa of map A to x alpha. So for example, let's take an element f in pi n of map A of x kappa. This is just a homotopy class of a map from sigma n A to x kappa. And therefore, these factors through x alpha for some alpha less than kappa. But then its image in x alpha plus 1 is 0, because in x alpha plus 1 we have killed everything of this form. And so its image in pi n map A x kappa is 0. And this proves claim 2. So you see, once we have the proposition, constructing the localization is just a basic transfinite recursion argument.
Can you scroll up to the beginning of the proof for a second?
Yeah. So I have here.
Okay. Okay, thanks.
So we construct this transfinite sequence, so x alpha, where at every step we kill all the maps from all the suspensions of A. And then when you get at level and these are by definition E equivalences. So we just need to show that at some point we get some E local thing. And that's because A is kappa small for some kappa. We don't know how big it is. It might be huge. We don't care. Some kappa will exist. Okay? Good. By the way, this proof is secretly basically the proof of the adjoint functor theorem in our setting, if you've seen it before. The hypothesis that this proposition I'm about to prove is essentially an accessibility hypothesis for the category of equivalences, which is one hypothesis in one of the versions of the adjoint functor theorem. But I don't want to do the general theory. I'm just going to do this special proposition. So let's go back here. Let me copy the statement of the proposition. And let me go back here. And let's prove. Okay, before I go through this proof, are there questions? Okay, so I will reduce this proof to a different proposition, which essentially is telling us that, so let's fix now X an E-acyclic spectrum, and we want to construct it. And the goal here is to show that every homotopy class of X can be seen by small E-acyclic spectra. So what I'm going to prove first is the following. So for every class, let's see what I want to call it. I call it F in pi n of X. There exists W, kappa small acyclic spectrum with a map W goes to X called G, such that G lower star, such that F lifts to pi star of W. This is the key point in this proof. I can see all homotopy classes. So note that if I didn't have a cyclic here, it would be trivial. I could just take a sphere. But of course, spheres are basically never E-acyclic. So I can show that I can add a few cells to this sphere so that it becomes E-acyclic, but I don't need to add too many cells. My cells are bounded by this kappa. So to prove this proposition, first I have a remark. So suppose that F is a finite spectrum, then the cardinality of the homology is less than kappa. And that's proven as we did last time by showing that the set of spectra such that the cardinality of their homology is less than kappa. Remember, the homology is the homotopy groups of the tensor product. Is closed under finite direct sums and cofiber sequences. And it contains all the spheres by our hypothesis on E. So, okay. Okay, let's do the thing. So we'll construct W as the colimit. W0 goes W1, etc. goes to X. Where at every step we're going to add a few cells. And we start with W0 sigma n of S. And this map is going to be our F, which I'm going to call G0. So this G0 works perfectly, except that its source is not acyclic. So, well, let's start to fix that. Suppose we have, and then sorry, we will construct it so that the map E star Vi goes to E star, sorry, Wi plus 1 is the 0 map. Sorry, such that the map, your map, because then this implies that E star of W is the colimit over I of E star Wi, which is 0. Because I'm taking a colimit of a bunch of stuff, which is probably non-zero. It's probably huge or whatever, but the transition maps are always the 0 maps. So at this point, we just have, so we have Wi, and we need mapping to X with Gi, and we need to construct just a factorization through a map that's 0 in He homology. Well, but that's now easy. So let Fi to be sorry, yeah. Yeah, no, sorry, that's not the point. The point is, now note that Wi is some colimit, now J in J, of Fj finite spectra, and J filtered. This is the omega case of the theorem we proved last time. So the homology is just the colimit of the homologies of the Fj. So for every little x in E star F, and yes, here I mean a homogeneous element, if you're curious, we can find an Fx finite with a map Fx to Wi such that X is in the image of Fx to E star Wi. Because X comes from some element in this colimit. So now we can take the sum for all x in E star Wi of Fx. And these maps to Wi. And note that this is kappa small, because E star Wi has cardinality less than kappa by induction, and all fx are finite. Yeah, I should have said that in the induction I also want cardinality of E star Wi less than kappa. That's an important element in the induction. I should mention it. Okay, sorry, let's go back. So we have this map. Oh, sorry, I made a mistake. I'm sorry. I shouldn't have taken Wi. Yeah. Okay, sorry, I made a mistake. I shouldn't have taken Wi, but Wi bar, the fiber of the map from Wi into X. And then these for W bar. And note that since X is E acyclic, the map from Wi bar to Wi is an equivalence in E homology. Yeah. I'm sorry. Let me pause for a second because I made a mistake in this construction. I was confused because their homology is the same, of course, but the spectra are different, so I need to use them. I can put a bar here, even if it doesn't change. Sorry for this mistake. Is the proof clear with this correction so far? So I can take this. And I can take the co-fiber. Of this map. And sorry, and the reason why I need to factor through Wi bar is that so that now this composition, let me purple, is canonically null homotopic, because I can use the null homotopy of the map from Wi bar to X. And so it factors through Wi plus 1. Sorry, I forgot this technical point.
Sorry. So at some point you said that it follows that for all x in E lower star f, what's big F? Shouldn't this be Wi bar?
Yeah. Yes, it should.
Okay.
Thank you. Sorry, that happens because I didn't manage to print my notes, and I am occasionally glancing at the screen with the notes, and occasionally, so I lose pieces of the proof, even if I wrote the notes myself, but still. Okay, but it's clear the construction of Wi goes to Wi plus 1. And the point is that by definition, this map is surjective in homology because, well, we constructed it so that it is. And this is an equivalence. So this map is the zero map in the long exact sequence, as we wanted. since its kernel is the image of this map here, which is surjective by construction. And now, and the cardinality of E star Wi plus 1 bar, sorry, no bar, is less than kappa by the usual argument that it fits between two things that have cardinality less than kappa. Okay. So that is the proof of the second proposition. So remember, the second proposition was saying that for every E-acyclic spectrum, you can find you can lift all its homotopy classes to some E-acyclic spectrum, which is kappa small. So now we are ready to actually prove our proposition. So proof of proposition. Are there questions so far?
Can you again walk us through the argument of the last diagram? So you apply
okay.
E star on everything? No.
Oh, here? Yeah, okay. So I need to prove two things. So okay, now this guy is clearly kappa small because it's the co-fiber of a map of kappa small spectra. I need to prove, well, this fact, which is kind of tautological, that it's not tautological, but it's actually true for every kappa small spectrum, that it's homology, E homology has cardinality less than kappa, so probably I should have just assumed that. And then this map is 0 in homotopy. But then this is constructed as a co-fiber. So this map is 0 in E-homology means that this map is surjective on E-homology by the long exact sequence. And this map is surjective on E-homology by construction. Because I literally took every class here and lifted it to some finite spectrum. And I am using that this map is an equivalence on E-homology, of course. But that, I mean, I have to use that X is acyclic at some point. Otherwise, the proof would be highly suspicious. And here is where I'm using it. And then, okay, then I have this thing such that all the maps are 0 on homology, and all spectra are kappa small. So I can take their filter colimit, and yes, here I'm using kappa uncountable actually, because I'm using that a filter colimit, sorry, that a sequential colimit of kappa small objects is still kappa small. So maybe I should, well, let's assume kappa uncountable for this argument. As you see, we're always allowed to enlarge kappa, so that's not a big deal. Okay. And now finally, we can prove the main proposition and close the circle. And now the proof is identical to a proof you've already seen. So let J be the category of, well, the infinity category of kappa small acyclic E-acyclic spectra with a map to X. So J is a subcategory of this fiber product. Fiber product of categories. Sorry, it's actually equal to this fiber product of category if you want. Then we can take the colimit for W in J of W, and this has a map to X. And our claim is, well, first of all, claim J has all kappa small colimits. And that's because kappa small E-acyclic spectra are closed under kappa small colimits. And so J is kappa filtered. Okay, this claim is easy. And the other claim is this map is an equivalence. And okay. As before, it's enough to prove this. And note that here I am using that this map is an equivalence. Here I'm using that J is kappa filtered. Because pi star doesn't commute with colimits in general, but commutes with filtered colimits. So even if for the proposition I didn't care that the colimit was kappa filtered for what I wanted to use it, I still need to use it in the proof. And okay, we know it's surjective. By the proposition we just proved. Proposition we just proved, it literally says that this map is surjective. That every class here can be lifted to the class here for some W. So now let's take an element in J and F in pi n of W such that GF is 0. And we want to show that this dies maybe not in W, but in some further element of this filter system, the kappa filter system. And does it work? A second. Oh yeah, that's very simple. So we have this map, F goes to W, goes to X, and I can take the fiber F of G. And this composition is 0 tells us exactly that this map factors in some way, non-canonical, but we don't care, we lift it somehow. That is to say, we choose a null homotopy of GF. And now note that F is E-acyclic, since W and X are, let me call it this F bar, this lift. So, by the proposition, we can find W bar, kappa small E-acyclic, with a map G bar from W bar to F, such that F bar lifts to, I don't know, F double bar, I guess. This is possibly not the best notation. So I have these, and this was whatever. I can call it H, doesn't matter. Now W bar is kappa small, and GH has a canonical null homotopic. Since it factors through F. So I can take W prime, the cofiber of W, and I can factor G by some G prime. This is the kind of game we've been playing for a while. Maybe it looks complicated to copy, but it's really some kind of diagram chasing in the end. G and factors through W prime. And okay, and let me call this, I don't know, AK prime, H prime. And now, okay, now G prime, H prime, F is the same thing as G prime, H, F double bar, which is 0 because this nice guy is 0. Oh, and this is kappa small because it's a cofiber of kappa small things. The end. This is essentially the same proof as the proof that every spectrum is a kappa filter colimit of kappa small spectra. Only done for acyclic spectra with the help of the proposition we just proved. And this closes the circle. And now we have the existence of bounded localizations. Okay, so we are roughly halfway through the class, so it's good because it means I get to give you at least one of the two main examples of bounded localizations today, which is a good thing. Questions about this proof I just did? Okay. If there are no questions, let's go to the first example. Inverting primes. So I decided to first do the example where I invert only one prime, and then to do the example where I invert a family of primes, even if the proofs are basically the same. But I think it's helpful to see them first in the case where you invert only one prime. So now let P a prime number. And in fact, it doesn't really need it to be a prime number. I'm just doing it in the case of a prime number, I don't know, for tradition, I guess. Remember, we defined this spectrum here, it's the colimit of the multiplication by P map. It has the property, this is called the Z1 over P Moore spectrum. because it has the property that its homology is Z1 over P, one star is 0 and 0 otherwise. I actually should probably put a word of warning here. For every abelian group A, you can construct a Moore spectrum, and it is unique under certain hypotheses, but this construction is not functorial, contrary to the case of the Allenberg-MacLane spectrum. You cannot have a functor. I'll probably put in the exercises for next week, though, not the one that will appear shortly after this class. And maybe when I'll talk about completion, I'll explain why it cannot be functorial, which is an annoying fact, but it's a fact. It's something we have to live with. But this exists without any doubt. And okay, the goal now is to study LS1. So the first remark is what is the homology of this guy? Well, this is just a colimit of the multiplication by P map. And so this is the homotopy of the spectrum with P inverted. In particular, and let me try write it as a lemma, a spectrum X is S1 over P acyclic if and only if P acts locally nilpotently, i.e. On pi star of X, i.e. every element of pi star of X is P power torsion. And this is just a statement about localization in classical module theory. But I wanted to state it clearly. So from these, we deduce the following lemma. So a spectrum X is S1 over P local if and only if P acts invertibly. On X, or equivalently on pi star of X. The multiplication by P is an equivalence, or if you want every element is uniquely P divisible, choose your favorite statement. Okay, and here goes the proof. So which direction is easier? Let's do first this. No. Actually, let's do first this implication. So the first remark is that S mod P is S1 over P acyclic. And that's because this guy is just a colimit. Sorry, it's a S1 over P, but P is an equivalence on S1 over P. So tough luck. Okay, now if P, now why am I doing this? Oh no, sorry, yeah, I'm doing the other implication. So if X is S over P local, then I want to say that S over P tensor X is 0. That's what it means P to act invertibly on X. i.e., multiplication by P maps is an equivalence. And now I'm going to do something slightly perverse and write these as the mapping spectrum from S to X, and this is the mapping spectrum from S to X. And I'm going to write this map as the multiplication by P map induced on the first component, because then the fiber of this map is map S over P X. And that is 0 because X is S, 1 over P local. And S over P was S 1 over P acyclic. It's kind of a perverse way of writing this, but it is. Okay, that's one implication. Now let's do the other implication. The other implication works like this. Suppose P acts invertibly on X, then the map from maps X over Px into X given by precomposition S1 over P, S is an equivalence. Why is this the case? Well, remember S1 over P was this colimit, so maps S1 over Px is the limit of map Sx, map goes in the other direction, multiplication by P, etc. And this map is exactly the projection onto the first factor, but these are all equivalences. So this map is in fact an equivalence. Now let W be acyclic. We can write this slightly crazy chain of equivalences, but not too crazy. So I can first replace X by these maps from S1 over P, comma X. And then I can use the adjunction property. And then use the fact that W is S1 over P acyclic. And this concludes the proof. Okay. This proof is probably not proving anything surprising to anyone, but it's slightly tricky. If you try to do it the first way you think of it, it doesn't quite work. All the steps are trivial, but you have to do them in the right order. It's one of those things. Okay. Questions about this result? No? Good. So now we can prove that, well, I'm calling it a theorem, but it's overly selling it. The map from X to S1 over P tensor X, which from now on I'm going to call X1 over P, exhibits X1 over P as the S1 over P localization of X. And to prove this, we only need to prove two things. So the first thing is that this guy, S1 over P tensor X, is S1 over P local by the criterion above. We can look at its homotopy groups, and P indeed acts invertibly in its homotopy groups because, well, we constructed so that the case happened. So it's enough to show this map is S1 over P equivalence. And this is, well, this is not hard, but let's actually see how it works, because that's right-hand side is a colimit. And since the fiber of this map is actually going to be important in the story of P completions, let's go through this carefully. Okay, for now I'm going to we'll look at this map as a colimit of S1 over P equivalences. So X is going to be the colimit of just the constant diagram at X, but X1 over P, remember, so that X is the colimit. It's the colimit of this map multiplication by P. And so in order to make the diagram commute, I have to add multiplication by bigger and bigger powers of P. That is, this map is the colimit of the map multiplication P to the n. So we're going to show that these are S1 over P equivalences. Why is that? Well, their cofiber is X tensor S mod P to the n. So it's enough to show S1 over P tensor S mod P to the n, which is S1 over P to the n is 0. But this is clear because P to the n acts invertibly on S1 over P. One word of warning. We have seen that every element of pi star S mod P is P power torsion, because this is an S1 over P acyclic object. It's not P torsion in general. That's a crazy fact, but it is true. In fact, one can show it is P square torsion. however. And in fact, as it happens, let's see if I recall, I hope I'm recalling the right degree, but pi 1 of S mod 2 is Z mod 4. It's easy to show that it's an extension of a Z mod 2 by another Z mod 2, and you might be tempted to assume it's a Z mod 2 times Z mod 2, but it's not. This is an instance of a topological rather than algebraic behavior of spectra. If you do it in chain complexes, if you take a chain complex and you take the cofiber of the multiplication by 2 map, you always get something whose homology is always 2 torsion. But in spectra, that doesn't happen. You have to go back to p² torsion. Okay. And this is actually what impedes the functoriality because of S mod 2. Oh, sorry, of Moore spectra. But I would say we will discuss this later, or probably I'll give it as an exercise. Because if the Moore spectra were functorial, it would be quite easy to show that all the homotopy of S mod 2 would be 2 torsion, but it's not. So, tough luck. Okay. So I'll put another remark. It's a very important one. So the map from LEX, you always have, sorry, actually, let me see. There is always a map from X to LE, the sphere tensor X, which is just obtained by tensoring by X the canonical map from the sphere to localization, which is always an E equivalence. That's easy to show because the fiber is X tensor some E acyclic spectrum, and so it's E acyclic. When the target, sorry, is E local for every X, this implies that LES tensor X is the E localization of X. In this case, the localization is called smashing. Sorry, let me spell. Yeah. It's called a smashing localization. That's because the old name for the tensor product of spectra is the smash product. And we have seen that the S1 over P localization is smashing. Not all localizations are, and the next example will be a localization which is not smashing. Smashing localizations are particularly well behaved. For example, E-local spectra are closed under co-limits, which is not a general feature of E-local spectra. And in fact, we more or less know a complete list of all the smashing localizations, though more or less in the sense that it's dependent on a very open conjecture, which might or might not be false. And actually, if you ask me, I would bet on the falsehood rather than on the truth of that conjecture. And so the smashing localizations, we don't really have a description. We can sandwich them between two smashing localizations, and the conjecture is that they're the same, but they're probably not. But they're the same on finite spectra, so in some sense, we know all the smashing localizations. But yeah, I'm not going to say more, except that we will see another example of a smashing localization later without many proofs, unfortunately, because it will get more complicated. And it is not going to be an algebraic case like this, where you just invert a few primes. But you can think of smash localizations as inverting higher elements in some sense, which opens the door to the periodicity phenomenon. But okay, let me first tell you a minor generalization of these S1 over P localizations, where I have a set of primes now. So let S, P1, P2, etc. a set of primes, possibly infinite. That's allowed. You can define S with S inverted as the colimit S P1, P1, P2, P1, P2, P3, etc. Adding one more prime at every point until I run out of primes. And then I just keep the one I have. Or maybe I never run out of primes. That's possible. And then, as before, pi star tensor X is pi star of X with a set of primes inverted. This with the same proof. And the same proposition with the same proof applies. A spectrum X is S inverted local if all prime in X primes in S act invertibly on X. I won't repeat the proof. You have to do the same proof, only instead of just S mod P, you have to work with S mod Pi for all I. But and with the same proof as before, you see that the map X goes to S tensor X, which I'm going to write X S inverse, exhibits the right-hand side as the S inverse localization of X. If you want, I can enter the details, but the proofs are literally the same. In fact, I had my notes open on the wrong page, and I was following the proofs of this proposition in the notes instead of the proofs of the previous ones, but they're really, really the same. And the reason I introduced these more general things, except that they exist, so it's always important to give examples, but I can take S to be the set of all primes, in which case X S inverse, it's often written as XQ, and it's called a rationalization of X. And here I'm going to have to use again that theorem by Serre that I mentioned last time. And I have that pi star of SQ is pi star of S tensor Q, which is Q in degree 0 and 0 everywhere else. Because all other homotopy groups of spheres are finite groups. In particular, this implies that SQ is HQ. And the goal of these is going to say that rational spectra are sort of algebraic. I'll state a precise theorem in this sense later. I won't be able to prove it, unfortunately, but I want to prove some results in this direction. In fact, the first result is the proposition. So let X be a rational spectrum. Then there exists an equivalence X with the direct sum of H by N of X. So X is a generalized Amberlake-MacLane spectrum. There are no fancy extensions, no fancy weird things that happen. We're rational and everything splits. Okay, questions about this? I'm going to prove it in 1 second. And I'll give you a consequence that maybe you didn't expect. Sorry.
Well, maybe not a question, rather a confusion. So you said that by
sorry.
Serre's theorem,
I forgot.
only this special homotopy group of the sphere is only one homotopy group of the sphere is infinite, right? Not two of
Yes.
them. Okay.
Well, I
because
stated the
those are
Serre's theorem. I stated the Serre theorem for the unstable homotopy groups, in which there is another one that's infinite. For example, the classical example is pi 3 of S2, which is Z. But when you go to the stable range, this becomes a Z mod 2, so it becomes finite.
Okay, great. That was the confusion.
I gave a precise bound. It's non-zero, only pi n of Sn and pi 2n minus 1 of Sn. And when you go in the stable range, only pi n of Sn survives the other die. If you look at the estimated horizontal suspension theorem. This actually can be better understood using rational homotopy theory, but of which this topic that I'm talking about right now is actually a start, but I don't think I have time to say anything more than this.
Okay, thanks.
Okay, let me prove the proposition. So the point is to construct maps sigma n h pi n of x to x iso on pi n. Because then you get a map from the direct sum, which is an iso on all pi i's, and you win. Now, pi n of x is a Q vector space. Because, well, it's a Q module, so it's a Q vector space. So it has a basis. Let me call it EI, IN. And we have a map. Sum I in IN and S to X, which is just EI. But now this is rational. So these, by the universal property, factors through the rationalization. And also remember, the rationalization is a left adjoint, so it commutes with colimits and everything. And what it boils down to is that the rationalization is just the sum of the shifts of the rationalizations of the sphere, since this is a smashing localization. So, and this is sigma n h pi n x. by definition. And this is the map, the required map, which is on ISO on pi n, and well, 0 everywhere else, because this Eisenberg-MacLane spectrum doesn't have any other homotopy groups that can go anywhere else. So this is the proof of this theorem. And as a corollary, let me give you an interesting fact. Well, Ku rationalized is the sum for n in Z of S2n of HQ. Because if you remember, we saw the homotopy of Ku. And well, it was Z in each even degree, and when you rationalize, you get a Q. So we have a map Ku to this guy. And I'm not talking much about ring structures, but from the fact that it has meshing localizations, it also follows that it's a ring map. But I'm not going to enter this. I'm just mentioning because which is called the Chern character. So H. And then we can easily prove this proposition. Let X be a finite space, even a finite spectrum, but I'm stating it for spaces since that's the setting in which it's usually stated. For example, take a compact manifold. Then you can take the Ku homology of X rationalized, and that's equivalent to, well, greater than or equal to 0, H2n X comma Q. Now, this is a bit unsatisfying because what someone would like to have is also an explicit formula for this Chern character, which exists, but I'm not going to be able to talk about it, but it's very, very explicit. I like the treatment in Milner and Stashev, but you can find it everywhere. Also the Wikipedia page on Chern character, presumably. But it is fun to see that this stuff exists just for abstract, trivial reasons. Even if, of course, it's not satisfying for computationalist perspective to just have this. And in fact, I'm doing it Ku because it's the historically important example, but this works for every spectrum, of course. I'm using nothing about Ku here. So you can do this story for every spectrum. So actually proof, well, since X is a finite space, maps sigma infinity plus X blank commutes with filter colimits. And so Kux rationalized, which is just the mapping space, sorry, the pi note of the mapping spectrum. Oh, sorry, I should. And then you can move the rational inside since everything commutes with filter colimits and rationalization is a filter colimit. It's just a colimit over this product of PIs. Oh, and this was a wrong. Sorry, I should have said product, not direct sum. Here. Apologies. That was this. No. Direct sum. Never mind. And yeah, okay. I don't know why. HQ. And now I can bring the filter colimit outside again. And this is exactly what this is. And okay, I have n greater or equal than 0. That's just because the negative cohomology of a space is 0. The more canonical way of writing it would have all n in Z, but of course, these are just 0 groups. And that's fun. That this thing exists, and it exists for such formal reasons. Of course, again, I'm slightly cheating because what would be interesting is to give a description of this map in terms of Chern classes, which is the original definition, but I won't have the time to do the theory of Chern classes here. But still. Okay. Yeah, I think I'm out of time. Oh, I just want to say the precise theorem in the sense that the rational spectra are algebraic. So it's a special case of a theorem by Schwede and Shipley. I'm not exactly sure if this particular special case was proven before. But let me attribute it to them. Although this particular special case, again, was probably suspected, if not proven, well before them. So the infinity category SPQ is equivalent to the derived infinity category of Q, which if you've never seen it before, it's obtained by the chain complexes of Q vector spaces, and you invert the quasi-isomorphisms. So this is completely algebraic. No, 2 dots should be here. So in this sense, rational homotopy theory tends to be very much algebraic in a very precise sense. And this is true for like this classical stable homotopy theory. There is also an unstable version of this theorem, and there are equivariant, motivic, and so on variants of this theorem. In general, when you have rational coefficients, stuff tend to lose all the topological information. And ultimately, the reason is that theorem by Serre, that rationally there are no higher homotopy groups on the spheres. This theorem is not that hard to prove actually at this point, but it would be a long digression. And it was one of the dream theorems I wanted to do in this class, but I don't think I'm going to be able to cover it, unfortunately. Okay. I think I'll stop here, and we'll talk about completion at primes next time instead. Are there questions? Okay, if there are no questions, have a nice week, and let's see each other on Thursday.
Bye.
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 Bye.